We are here for an interview with Michael Garland, who's from NVIDIA, for the College Will workshop. Our primary theme this year is productivity, and we will be discussing productivity from the point of a research organization in an industry with Michael Garland here. Michael, would you like to go ahead and introduce yourself, please?
Sure, thanks, and thanks for inviting me to the workshop virtually. To give you a sense of where I'm coming from, I joined NVIDIA back in 2006. Since that time, I've been a member of NVIDIA Research, and I currently lead our research group focused on programming systems and applications research. And the kinds of problems that I've been interested in for this entire time since I joined NVIDIA are basically, how do we enable people to take advantage of modern machines, which are highly parallel and increasingly heterogeneous, to solve the problems they want to solve. You know, programming on sequential machines is pretty well understood at this point. Programming on these more modern parallel machines is something that's not nearly as well understood. And there are a lot of gaps in the software ecosystem and the tools that people have had compared to the past. And so developing technologies that would help people take advantage of these systems is fundamentally the research problem that I'm most interested in.
That's great. Thanks for taking the time and talking to us. Let me start with the theme of the workshop, which is productivity this year. How would you define productivity within what you do?
It's a good question, and it's it's a hard one to give any kind of objective, quantifiable definition to, right?
Yeah.
But for me, productivity has always been about how easily can developers accomplish their goals, right? How much effort does it take to answer the questions they want to answer, produce the artifacts they want to produce, things of that sort. And productivity is basically when it's as close to effortless as you can make it, right? And I think that there are three key aspects of that that are somewhat qualitatively different in nature. So, you know, one aspect of productivity is sort of the processes that we use in the practice of software engineering, right? How do you go about organizing teams? How do you go about deciding on software roadmaps? What are the processes you put in place to support development? Another aspect of it is, of course, the people, right? Do they have the right skills, the right knowledge, the right mindset and approach, and so forth? And then there are the tools. You know, if you think of software engineers as crafting software, as with everyone, you need the right tools to craft the artifact you're trying to craft. And you know, in my own research, it's naturally this aspect, this question of, do I have the right tools for the job? That's the thing of most interest to me.
So that's great. That actually leads to my next question. So what are the tools that you like for improving productivity? Are there any specific recommendations you have?
Yeah, so that's a great question. And for me, the thing that has been kind of a central organizing theme for a long time is kind of the question of, how can we scale the practice of parallel programming beyond the very low-level nitty-gritty details of things like threads, for example? Yeah. Right, so everyone who's done any kind of computer science degree or taking computer science classes, the way that traditionally we taught people about how to think about parallel execution on modern machines is to start by talking about threads. And what do you run in each thread, and how do you synchronize threads, and the problems that creates, data race conditions and so forth. Yeah. And you know, that's kind of feasible when you're trying to manage a handful of them. But if you look at modern systems, there are so many threads to manage that it's very difficult for humans to really do that effectively, right? And I was preparing a talk last spring on a related topic, and I decided when I was making some slides to just glance and see how many threads were running on my laptop as I was running PowerPoint preparing some slides. And I think the total number of threads on my laptop, which was basically doing nothing other than running PowerPoint, was like about 2,500. Right? And if you look at the processors that NVIDIA builds, you know, there are 100,000 threads or more that can be co-resident on one GPU. So this question of how can we help people manage this complexity has always been particular importance to me. And one of the things that I've been really interested in and that we in my group have focused on to one degree or another is how can we provide higher level, more natural levels of abstraction for programmers in notations they're already familiar with, but that yet can be mapped onto efficient execution. So I can give you two examples of what I mean by that. One, for a long time, we worked on this C++ library that was called Thrust. It's part of NVIDIA's software platform. And it's modeled after the standard algorithms in the C++ library. And the insight that originally drove that was that if you look at C++ and its standard library, a lot of the algorithms there are inherently parallelizable. You know, if I call a function to sort some data, and I provide a vector of elements to sort, that implementation could be sequential, it could be highly parallel, it could even perhaps take advantage of very custom special purpose hardware or FPGAs or something like that. What was lacking though is any standard mechanism for the programmer to say that that's okay. Yeah. So over time, we worked on this proposal to introduce support for parallelism in the C++ standard library. And in the 2017 standard now, that was actually introduced into the standard library. So we're at a point now where if I am a C++ programmer and I'm used to using these tools in the standard library, I can now call functions like for each or sort or reduce or things of that nature and ask that they be executed in parallel. And I don't really have to change a lot else in my program to achieve parallel execution. Yep. Now it's hardly it's not a solution to all the problems, right? Yep. But it's a very useful tool to have. And for a certain class of applications, that's exactly what you would like. Yep. Another example of things we've been doing recently is a project we've been working on called Legate, which aims to take programs that use NumPy in Python and transparently accelerate and distribute them over as many GPUs as possible. And the real core of that approach is, again, you know, to identify a style of programming or a notation, in this case, NumPy, where people already use it extensively and its fundamental operations lend themselves to execution on complex machines, including, you know, large multi-node systems with 16 GPUs per node, many hardware resources. So this theme of understand the ways in which people already use systems, where there are opportunities to introduce high performance execution relatively transparently by the addition of clever system software or programming model frameworks. That's the thing that's been of particular interest to me, because it means that people can use these tools with the knowledge they already have. They don't need to learn dramatically new things. They don't need to write dramatically different programs.
That is great. It's great to hear. And if I can abstract it out one level up, the way you are talking about, did I understand it right? You are talking about abstractions that can easily be adopted into existing models. And then you are also interested in standardization of some of these approaches in C++ and other standard vendors.
Right, yeah, so I think that for tools like this to be successful, they need to be accessible to mainstream programmers, right? So one of the reasons that we wanted to embed these parallel algorithms in C++ is because it's a widely used mainstream language that the developers we were trying to help already used. The reason that we chose to focus on NumPy for this distributed project is because, again, it's a widely accessible framework that people already use. So I think that choosing abstractions appropriately is very important, but it's also very important to look for what are the abstractions and languages that people already use where there is opportunity to deliver more to them. Because although it can be a lot of fun to design new languages with totally new concepts and abstractions, it's so much harder to get people to actually use it productively because there's a very steep learning curve for them.
Yeah.
Whereas if you can help them where they already are by accelerating something they already do, then it's much more attractive from the user's perspective.
Yeah, I agree. Right? That's well put. So what are the typical challenges you face in these kind of asking users to even adopt a little bit, right? Or even come in a standardization process. So in terms of perspectives from both sides, right?
Yeah. So the biggest difficulty is probably that it can never be totally transparent to the user, right? Yeah. So they cannot be completely oblivious to the fact that you're trying to provide a combination of both high performance and relatively easy to use programming tools, right? To take the C++ example, if I'm going to call a function that's going to sort my data in parallel, and I'm going to provide, say, a comparator operator for the data I'm trying to sort, which would be fairly typical. In order for that to actually work, I still need to basically promise that this comparison operator I'm using is not going to introduce any data races. And therefore, I need to understand what might introduce data races, or at least, where is the safe zone which I shouldn't wander out of, basically the world of pure functions and values, that I'll be safe, right? And similarly, even with higher level languages like Python and NumPy, there are ways that you can write a Python program using NumPy that are easy to accelerate transparently. And there are ways you could write it that it would be very difficult, right? So if you, for example, write loops over matrices that implement matrix multiplication with loops rather than just calling a matrix multiplication function, that's going to be far harder to provide interesting benefits to the programmer than if they just called the matrix multiplication function, right? So while we'd like to, in these kind of projects, meet people where they are, they still have to, they're going to need to know some things about what are good idioms and what are poor idioms and things of that nature.
And where do you see the most opportunities for us in the future to improve productivity on different hardware?
So I find that the thing on my mind at the moment that sort of most undermines productivity is this tension between making programs that can be efficient and achieve the performance goals we have to answer the complex questions we want to answer, and good software engineering practice, right? So, and both of these are aspects of productivity. If productivity is how long does it take me to get my solution, I need an acceptable level of performance because otherwise it'll take too long to get the answer I want. But also I need the right process for developing software. Otherwise my development process will take too long, right? So good software engineering methodologies tend to focus on creating the right abstractions and specifically encapsulating details inside software modules that the users of those modules don't need to worry about and can't see, and things of the sort, right? I mean, that's been the story of software engineering for decades. The problem is that whenever you're talking about performance, software module boundaries and encapsulation can often be performance hazards, right? If there's a cost to pay when I cross module boundaries or cross through encapsulation boundaries, there's this natural tendency to push people away from good software engineering practices. So one of the big issues, in my view, is this question of how do we build advanced programming systems that let people achieve the performance they want to achieve, but while encouraging rather than undermining good software engineering practices and composability of software modules and things like that, without which, the process of software engineering becomes fundamentally broken. And that's neither of those things is acceptable from a productivity standpoint, right? I can't undermine good software engineering practices. I can't accept low performance because both are going to prevent me from getting the answer I want.
Yeah. Okay, so we struggle with this question almost every day, so I'm totally with you on that. So any final thoughts on how this would play out? This what are your expectations? Anything that you haven't talked about that you want to cover?
So my expectation as far as this fundamental problem that I think is a question we need to address about composability is that I believe what this implies is that we need to be exploring new ways of organizing execution of programs, right? So a lot of historical work on improving the practice of software engineering has gone into the questions revolving around how do I structure programs? Right? We invented the notion of procedures and of modules and classes and other techniques that structure program source code and made it more manageable and more flexible and easier to write good components that could be reused and things of that sort. Going forward, the complexity of parallel and distributed machines makes me believe that what's fundamentally missing is appropriate new systems for organizing execution at runtime into similarly organized collections of work that can be managed. So some of the work that has been done on task-based runtimes, for example, and some of the Legion runtime work that people in my own group have worked on is an example of the sort of thing I mean. By introducing new concepts that let you organize the execution of programs, you can do interesting things on behalf of the user that you wouldn't have been able to do if you didn't introduce some of these organizing principles. So to me, one of the interesting research problems here is there are decades of work on organizing programs. There's been a lot of work in recent years on organizing how we deploy software with containers and technologies of that sort, for example. But what's lacking is sort of the thing in the middle, which is how do we organize execution as an application runs so that we can do things on the user's behalf to make them more productive and give them the tools that they want.
Are there any recommendations that you have for our viewers that they should particularly adopt a model? You mentioned a few examples in the interview. Is there a favorite of yours?
Well, as I mentioned, my group specifically has been doing a lot of work with the Legion runtime, so I like that for various reasons. I'm sure that there are other systems worth investigating. What I would most encourage people to do is think about what are the systems worth exploring, and in what ways would it make sense to organize execution? Yeah. Beyond simply very low-level things like threads or processes or things that don't really give you the ability to actually reason about how to schedule or place work and data or any of that sort of thing. Yeah. So I still see this as a somewhat open problem. We're doing a lot of work to apply techniques like that to programming systems like Python, for example. There's a lot of work to be done there. I hope, however, that interesting new tools will come out of that and actually help people write programs productively and answer the questions they want to answer without undue amounts of work.
Yep, that's very nice to hear that you're working on. There are new things coming as well. Are there any final thoughts before we finish the interview that you want to?
No, I don't really have anything else to add. Thanks again for inviting me, and I look forward to hearing what other people have to say about what makes their lives unproductive. Because I think that from the standpoint of research, understanding people's frustrations with what they have right now is always a great place to start for asking what are the right research problems to solve.
Yes, yes, thanks a lot. And we appreciate you taking the time and giving your perspective on productivity in this year's workshop. We have to do everything virtually, but hopefully we'll be back to our normal in-person one, and we hope to see you at that time in the workshop itself if you can make it. And thanks again for your time.
Thank you.
Mike, do you want to start?